So it's my pleasure to welcome Miles. He's a Ph.D. candidate in the Operations Research Center at MIT. He's advised by Juan Pablo Vielma, and he received his bachelor's in Applied Mathematics and his master's in Statistics from the University of Chicago in 2011. After that, he went to work for a period of time with Argonne before his doctoral studies. And right now, he's a Department of Energy Computational Science Graduate Fellow, and he continues to collaborate with Argonne, but also with Los Alamos on methodologies for large-scale optimization, drawing from motivating applications in renewable energy. He's the author of JuMP and a founding member of the JuliaOpt organization. So with that, I'll go ahead and turn it over to Miles.
Okay, is that set up correctly?
Yes, it looks great.
Okay, so thanks for the invitation. Thanks everyone for listening in. So what I want to cover in this talk is first an introduction to the JuliaOpt organization, what it is, and what our motivations were for coming to the Julia programming language. Then I'll talk a bit about 4 software packages. These are JuMP, MathProg Base, Convex JL, Pajarito. These are all open source packages which you can go download and use on your computer today. And the focus of this talk is really more on the infrastructure that we've built up in Julia for optimization. Is not really meant to be a tutorial for how to use JuMP or how to use any of these packages in particular, but I want to focus on kind of the bigger picture, how it all comes together, and what you might want to know as, let's say, an advanced user of JuMP, or what you might want to know if you wanted to extend or build on top of what we've done. So, what is it that motivated us to choose Julia? Basically, in 2012, when Julia was first announced, I was programming in C++ and Python at the time, and at the time, if you wanted to write down an optimization problem, let's say solve a large linear programming or mixed integer programming problem within a programming language, and there are some reasons why you might want to do that. Say you want to embed your programming, you want to embed your optimization problem within a larger simulation. You want to build your optimization model programmatically. Those are things that are kind of awkward to do from if you're using more standalone modeling interfaces like AMP or GAMS. So let's say we want to build an optimization model in a programming language. The state of the art was Python and C++. And Python is great. It has a lot of packages for modeling, but pretty often it ends up that more often than not, it might be that building the model, or there are aspects of your implementation which are too slow, which you have to go in, maybe re-implement it in another programming language, and that's really not fun at all. And then on the C++ side, well, I've personally written a lot of C++ code, but it really you shouldn't need to go into all the infrastructure of C++ just to write down and solve a nice optimization problem. And so that was kind of the trade-off that we were facing when Julia appeared on the scene, and it seemed like a good platform in order to build up optimization infrastructure that would help us solve this problem of being high level and obtaining performance at the same time. So another motivation that has brought some people to Julia in the context of optimization is people who want to develop algorithms and solvers for optimization within a fast, high-level language designed for numerical computing. And Julia is pretty, I'd say, pretty ideal as a language for that use case. This is a place where MATLAB has dominated historically, but Julia, it's open source. You can very easily extend it, and people have found that it's a convenient language to develop optimization software in. And then another motivation that has brought people to Julia is, let's say you'd like to develop a modeling interface for a specific class of optimization problems, and doing so within MATLAB really requires a lot of development effort. And programmers tend to be lazy in a smart way, at least, and would like to minimize the amount of work they put into building something. So why not choose a programming language that makes it easier to build user-friendly interfaces? And these are just some of the motivations. You might not agree with all of them, but this is what has brought some people to Julia. And so I came to Julia, a number of other developers and experts in optimization have come to Julia. And when we came there was nothing. It was just a programming language with really no support for optimization. And so we started out 2012, started building out infrastructure for solving optimization problems, and that led us to the JuliaOpt organization. So what is JuliaOpt? JuliaOpt it's a website. It's a GitHub organization that helps us organize and collaborate on software projects, and it's also just a community of people. It's the people who have worked on these packages and continued to collaborate and work on building up this infrastructure. And on top of, let's say, on top of the JuliaOpt stack, we have JuMP and Convex JL, which are two algebraic modeling languages, which I'll talk about. Below them, we have this package called MathProg Base, which is an abstraction layer over optimization solvers. So if JuMP wants to talk to CLP, it will go through this abstraction layer, which has some abstract concept of how do I communicate with a linear programming solver, how do I communicate with a nonlinear programming solver. So the stack here is what I'll be focusing on for my talk. So I'm going to assume that if you're listening, you're familiar with the concept of an algebraic modeling language, which is essentially that we're not talking about hand-coding derivatives, we're not talking about hand-coding coefficient matrices, we're talking about writing down an optimization problem in a math-like algebraic form and then having the modeling language take care of transforming it into the input format which these state-of-the-art algorithms and solvers want in order to solve the problem. So JuMP is a modeling language for linear, mixed integer, conic, which includes second-order cones and semi-definite programming, and then also derivative-based nonlinear optimization. So many of these features are supported by existing tools like AMPL, GAMS, Pyomo, YALMIP, CVX to a certain extent, and these are essentially the set of problem classes that JuMP supports now. We do have documentation, which is still a work in progress, but we encourage you to take a look at it. I'd like to just give one example of a nonlinear optimization model. So we have a collection of Jupyter notebooks, which serve as examples for JuMP and other JuliaOpt projects. And here is a JuliaOpt notebook describing how to model a basic rocket control problem with JuMP. And the goal of this optimization problem is to maximize the final altitude of a vertically launched rocket, where we can control the thrust of the rocket, and we have to take into account the mass, the fuel consumption rate, gravity, and aerodynamic drag. So I'm not a physicist, and I'm sure that many people listening have a much better understanding of this, the physics of what's going on here. But at least I'll be able to describe what the model looks like from the syntax level. So I'll skip through the dynamics. What it looks like is, well, this is actual Julia code. At the top, we import JuMP and IPOpt, which is our nonlinear solver. We create a JuMP model, and we say solver equals IPOpt solver, which will tell JuMP to use IPOpt. Then we define some numerical constants, some parameters, And where the JuMP code starts is with this def var command, which declares an optimization variable. Here we're declaring delta t as it happens to be in this model that actually the time step is an optimization variable. So this is one of our, let me zoom in here. This is one of our variables in the optimization problem. We also define state variables, which we keep track over. We index from 0 to n. And then our objective is to maximize the height at the final time step. We add constraints for initial conditions. We define some linear sub-expressions. We discretize and we do trapezoidal integration rules. So very, very standard stuff. We provide a starting solution. We say solve. We get the answer back. And since we're in a programming language, we can call out to another package to visualize the results. So here we're just calling another Julia package called gadfly. We call plot, and then we can very easily plot our solution. So you can see that this is the optimal thrust profile, which IPOpt returns to us, and it says to do maximum thrust for a period of time, drop down, ramp up a bit, and then shut down. So this is a very non-convex, non-linear optimization problem, but it is something that is solvable by a state-of-the-art solver like IPOpt. So I know I went through that very quickly. Please ask questions if I went too fast. Okay, so we do have benchmarks with other. So we did claim that Julia solves the issue of performance, and we have benchmarks with other modeling languages like Ample, GAMS, Pyomo, YALMIP in the paper that we linked there. And our main claim is that JuMP, in terms of the time that it takes to generate an optimization model, so all of the pre-processing that JuMP does in order to prepare the problem for the actual solver, which does the hard work, all that pre-processing time is about on the same order of magnitude as what these commercial tools do, and sometimes can be much faster than the Python and MATLAB-based tools. JuMP, as far as we know, it's been used for teaching in at least 10 universities, and if you're using it, please let us know. We're really happy to see that it's being used in classrooms, even though it is not a 1.0 software, and it still has at least a year or so before it becomes a 1.0 software. People have found that it's still useful enough that it's worth taking a look at. I'd like to highlight one feature of JuMP that very recently developed, which distinguishes it from maybe other nonlinear modeling languages which you've seen so far. It is the fact that JuMP can support automatic differentiation of user-defined functions. So what that means is you can write down a Julia function and register it with JuMP and then use it as part of your nonlinear optimization model. And this differs from traditional tools because typically there's some finite list of operations which are recognized, a finite list of closed form functions which are you are allowed to write down, and then you have to build your model on top of that. So we're starting to build up and kind of extend beyond what's traditionally supported by an algebraic modeling language. So here's a quick example of a Julia function which computes a square root by performing Newton's method to find the zero of the equation z squared minus x equals 0, and it does a pretty good job of finding an accurate numerical solution. So this is pure Julia code here, unrelated to JuMP. Then we call a JuMP function, register NL function. We say the name is square root. We say it takes 1, the input dimension is 1. We give a reference to the function, and then we pass in. So this is what is actually new here. We pass in this magical keyword called autodiff equals true, and then JuMP will use automatic differentiation techniques to compute an exact automatic gradient of the function they provided. So there are For example, Ample and GAMS do allow you to hook in your own custom functions as part of algebraic models, but what they will not do is compute gradients of them. So what we've built on top of this is saying, you provide your function, we will use some existing Julia techniques to compute gradients of your functions, and then you can go ahead and use that within a JuMP model. So here is the actual JuMP code. We declare an optimization model, we've defined two variables, we're setting an objective to maximize the sum of x, we're adding a nonlinear constraint where we're now using our user-defined function which we've just defined, and then we say solve. So what happens is that JuMP will take this algebraic model and take care of computing all the derivatives for IPOpt, essentially. And if you'd like to hear a bit about the methodology, the JuMP documentation talks about how we actually go about computing these automatic derivatives. And I'd like to highlight a new JuMP extension, which we just found out about. It's called multi-JuMP. And this is the first JuMP extension which was not created by one of the JuMP developers. So we weren't really aware about this until it was announced, and we're pretty excited to see people building up extensions on top of JuMP. So for example, this extension lets you specify a multi-objective optimization problem, and then has some methodology to help you compute the optimal Pareto front, for example. And this is all open source software that was built on top of JuMP. Also want to mention that we have a new book, and I believe I saw the author on the list of participants, that it's called Julia Programming for Operations Research. And this is a book that we just found out about a couple of weeks ago, and we're excited to see that people are starting to write some literature to help people get started with Julia, get started with solvers, get started with writing down optimization models in JuMP and Julia. So I'd recommend, if you're looking for a reference, I'd recommend taking a look at this book. Okay, so that's all I'll say about JuMP for now. Next, I want to talk about MathProgBase. So MathProgBase is this abstraction layer which JuMP and Convex JL use to communicate with solvers. So usually, if you're just a consumer or you're just a user of JuMP and these optimization solvers, you shouldn't need to care too much about our abstraction layers. It's kind of boring infrastructure stuff, but at the same time, it's really powerful. So when you should care about all this infrastructure is, let's say you want to access properties of a solver which are not exposed by JuMP or Convex JL. Let's say you want to query derivatives of a JuMP model, so we make it easy to write down and solve a nonlinear JuMP model, and if you want the Jacobian or the Hessian at the optimal solution or at any point you'd like, you can pretty easily do that, but you have to go and dig in and understand this infrastructure. If you are an open source developer or a developer at a commercial of a commercial solver package, and you'd like to write a Julia wrapper for your solver, you might have to, you will have to come in and understand this infrastructure in order to expose these solvers to JuMP or the whole JuliaOpt ecosystem. If you'd like to write a solver in Julia, and I'll show you a quick example of that later, then again, you have to understand our abstraction layer. If you'd like to create a modeling interface in Julia, we make it very easy to do so. You immediately have, if you're creating a modeling interface and you'd like to access all of the solvers that we've already wrapped, it's very easy. You just have to essentially support one solver and one interface for talking with solvers, and then you have access to all of our solvers that are supported in Julia. So it's, again, a very easy thing to do. And now that we're starting to develop solvers in Julia, you may want to access a Julia solver from another language, which is another reason why you might want to take a look at our abstraction layers. So if this doesn't apply to you, you can just skip to the next section, but I'd like to get this material out there because it's not something that's particularly well documented, and I really hope that people will see this and build on top of our infrastructure. Okay, so here's the hierarchy of packages that I showed before. On top we have JuMP and Convex JL, which are these two algebraic modeling languages. And the way they communicate with these solvers, as I mentioned, is through MathProg-base. So we have separate Julia packages. So Gurobi.jl is a Julia package, a small Julia package, which wraps the Gurobi solver. We have IPOpt.jl, which is a small Julia package, which wraps IPOpt. And these all implement a common interface, a common abstraction, and then the way that JuMP and Convex interact with these solvers is through that abstraction. So our philosophy, as I said, is to create a small Julia package which wraps a solver's C API. So Julia makes it very easy to interact with, let's say, a shared library. You can call shared libraries very easily. We write a small wrapper to access shared libraries, and then add on top of that a few more methods to implement our standardized interface. And if you've dealt with abstraction layers, optimization abstraction layers before, you might be skeptical because, well, as soon as you start abstracting, you start losing some contact with some specialized features which solvers support. And as soon as you abstract over that, you might be losing something. And our goal in defining our abstraction layer is to really make it not get in your way, just make it easier to abstract, but not prevent you from accessing low-level features. So you'll find that it's very easy to go in and access anything that is supported by, let's say, Cplex as a specialized option. You can go in and access that. We won't get in your way for doing that. So MathProg-base has kind of gathered, clumped around 3 different classes of solvers that we support. And these are, one, designing an abstraction. We have to, well, what do we abstract? What do we not abstract? We decided to essentially define 3 different problem classes which solvers may choose to support. And these you'll see that these problem classes really mimic the low-level interfaces that the solvers themselves do. So you'll see that to wrap a certain solver, you have to see, well, is it a nonlinear solver? If it's a nonlinear solver, it should be very easy to interact with this nonlinear wrapper. So linear quadratic it's a bit of an awkward name, but it refers to classes, the class of problems or the class of interfaces where the solver starts off with let's say, a linear programming problem, and then lets you tack on quadratic objectives, quadratic constraints, integer variables, all sorts of things like that. If you've ever interacted with Cplex, Gurobi, CBC, GLPK, then you've seen that this is kind of the way that these solvers view the world. So this is one of our abstractions for solvers that start off with linear programming and then lets you say, well, you can add a quadratic objective, quadratic constraints. This is one of our interfaces. For conic optimization, which may not be too familiar for many in this audience, it's a representation of convex optimization problems that turns out to be extremely powerful. You can essentially represent almost all of the convex optimization problems that arise in practice through conic optimization. And this is a very different interface where the problem is specified by saying that an affine function of your variables belongs to some convex cone, where that cone could be the positive orthant, the second order cone, positive semi-definite cone, exponential cone, power cone, and don't worry if you don't know what that means, but we have a few solvers which supports that interface. And then finally we have the traditional nonlinear derivative-based interface. So very classical IPOpt. IPOpt wants function evaluations, gradients, Jacobians, Hessians, and maybe some other solvers want expression graphs. So this is another interface which we have standardized around. So IPOpt, MOSEC, Nitro, and NLOpt are all solvers which take an input in this form. So what does this all mean for users? It means that, so for example, you can write down the same linear programming problem in at least 3 different ways. You can use JuMP, you can use Convex JL, and we also have a MATLAB-like linprog interface. And let's say we want to use the Coinoir CLP solver. All you do is say, using CLP, that imports the Julia CLP package. You pass in a CLP solver object, and that's exactly the same solver object that you use within JuMP, Convex JL, or linprog. So this all uses the same infrastructure to communicate with solvers. So that kind of makes it easy to kind of switch if you want to play around with different modeling languages. You want to write down the same model in Convex and same model in JuMP. You can do so, and it's easy to use the same solver in both cases. Okay, so you might be seeing this and say, well, how do I set solver options? You've created this abstraction. How do I really set solver options? Because I know that if I set this option, if I set this tolerance, then IPOpt will solve. If I don't, then it'll crash. So I really want to set this option. The way we do that is we do not abstract over solver options. You can essentially provide any solver options that the solvers themselves support and document. So if you go to the Gurobi documentation, any options that are listed there, you just pack them into this Gurobi solver object. So we don't provide any abstraction over that. Okay, so there's another case where maybe you want to access some property or some solution property from the solver which is not exposed by JuMP. So for quite a while, in MathProg base, we've provided a interface to a few low-level solver properties. So these are, let's see, get obj bound. So if you're running a branch and bound algorithm, you may want to ask what's the best lower bound that the solver found before it terminated, if it didn't terminate with an optimal solution, or the relative gap. These are things that you would, if you're solving in integer programming or integer convex, integer non-convex optimization problem, you might want to query this from the solver, and is not something that we have actually exposed directly through JuMP yet. So in order to get that, we've been telling people, well, we take the JuMP model M, we have to get the MathProg base model out of a JuMP model. So the JuMP has a function called getInternalModel, which returns the MathProg base model at the MathProg base level. And then you can ask MathProg base.get obj bound to, well, what is the best lower bound if we're minimizing. Okay, so this is what we've been telling people to do, and we've gotten some complaints, but because it's really not a very intuitive syntax. You have to maybe understand a bit too much about how JuMP works to get this very simple property. So I agree, yes, this is annoying. Why can't we just have lower bound equals get obj bound M, where M is your JuMP model? So what I'm going to do is live code and implementation of this fix, because we're responding to user complaints, and I'd like to give you a peek of the JuMP development process while we're doing so. Okay, so I actually won't live code it, but I'll show you how I'm going to commit the change to JuMP. So this morning I went in and implemented a fix, and it's a 10-line fix. We go through some methods in MathProg base, and all we're doing is calling, looping through a list of methods and implementing a little wrapper. So that's all that's there. And if you're familiar with Git, you'll see that these are the changes I've made to JuMP. They're not committed yet. I'm going to make a new Git branch, going to commit my changes. What should I call this? I'm going to push my branch to JuMP. This is how JuMP development works. And then we're going to open a new pull request. And I'm going to create a pull request. And this is issue number 772. So if you have any comments on it while I'm giving the webinar, you can go commit, comment on my code if I've made a typo. And then we'll see, we'll come back to this later. Okay, so this not abstraction over nonlinear optimization. What does MathProgBase do? MathProgBase provides an abstraction over the communication process between nonlinear solvers and users and modeling interfaces. So solvers want these oracles or callbacks to query gradients, Jacobians, Hessians, and these modeling interfaces provide, by some means, they provide these oracles for derivative evaluations, or users might want to hand code these derivatives. So since we've provided an abstraction layer, this means that if you write a solver in Julia that interfaces with this abstraction layer, then you can immediately access your nonlinear solver from JuMP. Which is obvious. What is less obvious is that we also have a little wrapper that lets you access Julia-based solvers from AMPL. So we have a wrapper which will read in, which will use AMPL as an oracle, as a callback for derivatives. So if you write a solver in Julia, you can access it from AMPL. And I have a little demo notebook of this, which I'll just show off very quickly. It's an implementation of Newton's method in less than 50 lines of code. It implements the MathProgBase interface. And we'll see this is the main body of the optimization algorithm. You see that we have methods for evaluating the Hessian of the Lagrangian. This is our Newton step. We have methods for evaluating the gradient. And this is almost good enough to use in a classroom, I'd say. So this is a notebook that you could take and show students how to implement Newton's method, and then you can immediately access it from JuMP. So there's no need to hand code derivatives in order to test out your algorithm. Okay, so that brings us to Convex.jl. So Convex.jl implements what's called disciplined convex programming. And this is very different from the traditional nonlinear derivative-based view of the world. It's a representation of convex optimization where it is your job to prove convexity of your convex optimization problem. So Convex.jl will reject your algebraic model if you have not satisfied its rules for proving convexity. So this is exactly the same philosophy as CVX, if you're familiar with that package, and CVXPy, which is an implementation of the same idea in Python. And behind the scenes, which this aspect is kind of less well known about CVX, is that it translates convex optimization problems into this conic form that I mentioned before. So any convex optimization problem that you write down in Convex.jl, what Convex.jl does is translate it into this conic form, and it'll call conic solvers, for example, semi-definite programming solvers, second-order cone solvers. That's the method that it uses to solve these problems. So here's just a little example of how to use convex to compute various standard textbook example of a maximum volume inscribed ellipsoid within a set of linear constraints. And what you can essentially do is declare optimization variables say that you want to maximize the log determinant of this matrix B, and log determinant is related directly to the volume of the ellipsoid, subject to the constraints which bound the ellipsoid by your set of linear constraints. So that's all that it takes to write down and solve this optimization problem. And behind the scenes, what Convex JL will be doing is translating this into a semi-definite programming problem and calling a semi-definite programming solver through the conic interface. So that's a lot of moving parts, but that's what happens when you write down this problem and call solve. Okay, so that brings us to Pajarito, which is a new pure Julia solver for mixed integer convex optimization. And by that I mean a convex optimization problem where we've added a set of non-convex constraints, but these non-convex constraints have the form that certain variables can take only integer values. So it's a generalization of mixed integer linear optimization, but we're also allowing convex constraints, and we say that the problem is convex after we relax the integrality constraints. So this is a solver. It was released very recently. You can go download it and use it. And what's interesting about the way that it takes as input is that it supports both nonlinear and conic input. So if you give a problem in nonlinear optimization form to Pajarito, it will essentially go out and implement a similar algorithm to what Bondmin does. So Bondmin is one of these, is a state-of-the-art solver for mixed integer convex optimization from the Coinoir world, and it implements what's called an outer approximation algorithm. So you approximate your convex constraints by a sequence of linear tangents, essentially. And then once you've approximated your convex constraints by linear tangents, you now have a mixed integer linear relaxation of your problem, and we can go hand it off to very efficient mixed integer linear solvers. And so we can essentially replicate Bondmin if you give it nonlinear input. If you give it conic input, then we implement what we call a new conic outer approximation algorithm, which is one of the first algorithms specialized for mixed integer conic optimization. And the reason why we care about mixed integer conic optimization is that it turns out that it's a very convenient representation of mixed integer convex problems, and it's actually a superior representation in many cases to the classical derivative-based input format. So if you'd like to know more about that, we have a paper posted on it. I could spend a whole hour talking about that. But what I'd like to focus on is actually what is it about the infrastructure that I've talked about which helped us build up the solver and get it out the door. So I said that MathProgBase supports 3 different modeling interfaces, 3 different categories of problems: as linear, quadratic, conic, and nonlinear. Pajarito accepts 2 of the 3. So if you provide a problem in nonlinear form, we implement the MathProgBase nonlinear input form. Oh, looks like we have some comments on the development issue. We have 4 thumbs up and 2 comments, so that's pretty cool. And so the tests are still running, so I won't merge it yet, but that is a live view of the development process. Okay, so back to this. We have take in problems in conic format or nonlinear format, and to do so, we implement the MathProgBase interfaces to nonlinear and conic optimization. So if you look at these whole files contain the full implementation. So if you look at the nonlinear implementation, it's about 700 lines of code. The conic implementation is, let's see, 1,200 lines of code. and it replaces much of the functionality, not all, but much of the functionality of Bondman, which is a large C++ project with tens of thousands of lines of C++ code. So that kind of demonstrates you can really very effectively implement optimization algorithms in much less effort than it would take to do in C++, and it's on top of that, it's very easy to connect with the infrastructure so in order to access these solvers from JuMP. And then finally, on top of that, since we have this infrastructure for talking to solvers in an independent way, we can very easily support more solvers than Bondman does, for example. So Bondman supports as a nonlinear solver. I believe it only supports IPOpt, and as a mixed integer subproblem solver, it only supports CBC or CPlex. And because we have the ability and we have this infrastructure to change out solvers, it means that you can take any mixed integer linear solver, which you'd like, any nonlinear solver or conic solver, which you'd like, and use that to solve these subproblems within our algorithm. And it's very easy to do so. And so this is not just really convenient, I'd say it's critical. As we were developing Pajarito, it became obvious that some of our nonlinear subproblems were crashing. It's numerical issues. I'm sure many people have experienced this before. Solvers might crash, and it was very easy for us to just plug in a different solver and move on to solving our problem instead of spending time trying to fix one particular solver. So this was really a critical feature for us to be able to run our experiments and get the solver out the door without being bogged down by convergence issues by any particular solver. So with that, I'd like to thank many of the people who have contributed to the solver infrastructure in Julia, or the JuliaOpt ecosystem in general. I may be missing some people, but it's not intentional. And I also have to thank the Julia developers. So this is a talk about infrastructure. We've built all this infrastructure on top of Julia's infrastructure, without which we'd be back in Python or C++, unhappily kind of developing software. Now we're very happily developing software. So I'll have to thank the Julia developers and Julia community for that. If you'd like to learn more about JuliaOpt, go to JuliaOpt.org. We also have a JuliaOpt Google group, so feel free to ask questions there, and someone will eventually get back to you. And with that, I'll thank the audience and start taking questions.
Okay, thanks, Miles. Excellent presentation. So now we'll open it up to questions from the audience. You can ask a question if you'd like to unmute your microphone, or you can post something to the chat window. So we'll go ahead and start with some questions now. So, Miles, I just had one question just to get us started. Yep. Now, I like the automatic differentiation features. What about, I've noticed in teaching optimization that sometimes students, just want to naively put in something like an if statement, something that solvers might have a hard time with. Does the automatic differentiation that you've implemented, does that do anything special with some of these functions that might cause a problem?
So we support if statements to the extent of, let's see, I'll just live code that. We support if statements there's a Julia command called Ifelse, so you can provide a condition and the value of the function if the condition is true and the condition is false. So it's kind of, so it looks like if else x greater than 1, where x could be a decision variable. So you can write down an expression like if else x greater than 1, x squared, or square root of x, and that is that is valid, and we can differentiate it obviously at the points where it's differentiable.
Fantastic.
Yeah, I mean it's up to the solver whether it wants to converge or not, but we can differentiate something that looks like that.
Okay, great. One question from George. Would you advise waiting until version 1.0 for some purposes in terms of Julia or JuMP?
Yes. If you are asking that question, then there are definitely cases where people might want to wait until a 1.0. It's possible that code you write today will need to be updated if you run it 2 years from now, which hopefully once a 1.0 comes out, that's the expectation is that code you write will last longer. It's Julia itself is still actively developing, so that's one of the reasons why we don't feel that we can release a JuMP 1.0 until there is a Julia 1.0. And until then, I would say yes, if you're worried about the longevity of your code and you don't want to spend the time updating it, you just want to write it and run it and let it run for 10 years, it's not the time to use JuMP or Julia. But that said, there are a lot of people who have found that it is useful enough to go ahead and use already.
Okay, fantastic. We have Camilla, did you want to ask a question? Your microphone is unmuted. Okay, let's go back to the chat. From Alex, any plans to support complementarity constraints in the near future?
We do not have plans for that because that's personally it hasn't come up in my own work, so it's not something that I would spend my own time to work on. If there's someone who's really interested in that, we could certainly work with them on coming up with a good way to extend JuMP to support them. But it's not something that we are currently working on.
Okay, great. And Ian, thanks for the chat. There are some companies who might have a higher need for long-term stability who are using Julia, certainly for research code. The timelines make some more sense if the utility is there for you. Okay, great. Bruno, I see you're unmuted. Do you want to ask a question?
Yes, thank you, John. Miles, thank you for your talk. I just have a quick question in terms of like industry acceptance of Julia and JuMP.
Yes.
Do you know anything? Have you heard of any companies that are using it or they're interested in it?
We've heard of. We have a few. I don't want to name them, but it's also it's open source software, so nobody really lets us know if they're using it. It's probably early for large scale industrial application, but there is at least one startup who's using JuMP as part of their core infrastructure, and we'll see how it goes from there.
Okay, thank you.
Okay, great. Okay, so another question from Joel. For the algorithmic differentiation of standard Julia functions, while loop example, does it implement the forward or reverse mode of AD? And also, what about higher order? Okay,
that is exactly the question that you should be asking. We implement forward mode because that's the easiest way to do so. We use a package called, there's a Julia package called ForwardIf, which implements forward mode automatic differentiation based on operator overloading. And this is obviously not the most efficient way to compute a gradient of a high, especially if the input dimension is high. So our use case here that we're targeting, at least at the first step, is for where these user-defined functions are generally low dimensional. They're not in the thousands of variables, but they're maybe in the tens of variables. And in that case, it would be not too bad to use forward mode. But there's definitely a cost to pay for if you write down the same model with user code versus in closed algebraic form. The closed algebraic form will lend itself for derivative computations much more than the generic user code.
Okay, great. Okay, so Tizen has a question. How does JuMP communicate with the solver? Is there writing of NL, LP files?
Okay, so for communicating with solvers, like for the solvers which are already wrapped, for example, IPOpt and Nitro, all the communication is in memory. So there's no intermediate temporary files, including for LP solvers, Cplex, GROB. We use their efficient in-memory APIs. We also have a package developed by Jack Dunn. So for the solvers that we do not have wrapped, that we do not wrap their C API, we have a way to communicate with them through NL files. There could be some performance penalty for that, but it does let you access the solvers. But by default, the core solvers are all in memory.
Okay, fantastic. And then Ian's comment there in the chat window as well. We know of one company using JuMP for rail scheduling, a multinational in the financial sector is using it, as well as the startup. Workforce scheduling, others are out there who haven't gotten in touch. So thanks for that comment as well, Ian. Okay, any other questions from the audience? I had one question from a grad student who was using Julia and JuMP and had been working with Python. Sometimes the startup time, just to when you're running a script multiple times and debugging, and you're running from the command line and restarting Julia each time, is a little bit slow. Is there any? I saw yours came up fairly fast. Is there anything you do to have starter or faster starting times just from initial bringing Julia up?
Yeah, so that's definitely an issue. It's an issue that's improved recently, but it's still an ongoing issue. So, for example, what you saw here, I had made some modifications to JuMP. So when it was loading, it first said recompiling, and then when I run it now, it's just going to launch the package very quickly. So there is some recent support for pre-compiling packages when you use them, but that doesn't quite fix the issue. So the issue is that when Julia runs something for the first time, it compiles it. So this is time that if you were using C++, you would see that this time is you first compile, and then you run it, and you know exactly if it's spending time on compiling or running. Here in Julia, the first time you run it, it will compile it, and then you might. So it's slow when you're doing something interactively. I'd say the best workaround for now is that if you're developing code, you can put it in a package and precompile a package, even if it's local. It doesn't need to be a publicly released package, but the infrastructure is there to precompile packages, and you could use that to potentially speed up your iterative development process. But it's definitely a recognized usability issue.
Okay, fantastic. Okay, so any other questions? Go ahead and unmute your microphone if you'd like to ask a last question for our speakers. And Ian, thanks for jumping on as well. We appreciate you. As Miles mentioned you as well as one of the developers, so we're grateful that you could join as well. Okay, well, thanks everybody for joining. It looks like we're out of time. I'll go ahead and post a recording of this later today to YouTube so that you can access it. And then also, Miles is available through email or other means if you'd like to get a hold of him. if you have questions for him offline. So grateful for everybody who could join, and we'll go ahead and convene until next time.
Cool. Thanks for